Hello everyone, welcome back to alkaline hydroxide 784, and today in the mathematics series we are doing the definite integral. So definite integral. So last time we covered integration techniques. So for the definite integral we are looking at a subset of integration. So if you just do integration without any range, you just get a function. But if you put a particular range, then you don't get a function, you get a number at the end of it. So let's get right into it. So in the previous episode, I talked about how integrals are generally like there's a certain they're like the opposite of differentiation, right? So if you want to look at it um, more fundamentally, a definite integral would be something like a sum, like the area under the curve from a particular point to a particular other point. So if you think about it, let's say you want to find the integral of the curve x squared from 1 to 2, and you can just draw x squared on the graph, then put x equals to 1, you draw a vertical line up, and x equals to 2, then draw another vertical line up, and in between those two lines you have an area. So what exactly is that area? I mean, you could just attempt to measure it with some instrument, but that's gonna be pretty hard. So what did the people, I don't know, Leibniz or Newton, whoever did calculus do? Well, what they did was that they put some kind of trapezium kind of thing under each. Like you imagine one big trapezium first, connecting the two lines. You know, the x equals to 1 and x equals to 2. You have a big trapezium there. And then afterwards you break it up into two trapeziums, and then not trapezium, rectangle, not trapezium. So you break it up into more and more rectangles until it's so minute, like you just keep making it bring it to infinity. In other words, you're trying to bring it to a limit of the sum of the areas of all of the rectangles, in a sense. So if you keep increasing the number of rectangles, you will get an integral, basically integration. And that's what is meant by the first point as the concept of a definite integral as a limit of a sum. So the sum here is the sum of the area of all the small rectangles that you can keep making smaller and smaller. As in not smaller, as like thinner and thinner. So you can keep increasing the number of rectangles in that can fit in the space of 1 to 2. And when that number goes to infinity, you're trying to get a limit, because obviously you cannot really count the area of all the infinity rectangles. So instead you represent it as a limit of the sum. So that's the idea of the integral. So how does this lead to what it truly is? Well, for x squared, well, we do know, like what I'm more familiar with is just doing the opposite of differentiation. So how you would use the fundamental way of getting the answer. In this case, since we have a definite range, you can consider, like for example, the step size. So you have the step size, which is maybe, let's say, b, and the height on the left. So for example, the very first one will be 1, and of course, and as you keep going, the height will keep increasing until 4. So if you think about it, yeah, this just I don't think I really learned that term. I learned the fundamental for differentiation, not really so much integration. I only learned how it was derived, but I didn't learn the exact derivation. So let's see. But anyways, it's not that, don't worry too much about exact way of writing down the derivation. Just understand that's just how it came about, okay? So let's move on. So now we know that definite integrals are like the area under a particular curve and with a particular range. So from x1 to x2 or whatever range that you give. And that's why when you write the integral, you must write the bigger number on top and the smaller number below. If you do it the other way around, you will get the negative of that constant, because that's just how they work, I guess. Because if you think about it, when you're calculating it, you'll be putting the bigger one minus the smaller one. So if it's positive, then if you swap it around, then the answer will be negative. And there's a reason why you can still get a negative answer even if you wrote it correctly, like the bigger number on top, because there are some curves that go below the x-axis, and if your area that you're evaluating is below the x-axis, the area calculated will be negative. And therefore, if you're calculating an area that has both stuff above and below, you may end up getting 0 because they cancel out or something, like a periodic graph, maybe sine x or something like that. That's why you should be careful when if you are trying to get the actual area of everything, then you must be a bit careful about it. But if you're just trying to find the integral, then it's okay, 0 is correct. But if you're trying to find the area under each of those parts, then you must instead do 1/2 of it and times it by 2, and you get the area in a sense. So yeah, that's one thing that you need to take note of. So now, how do you actually get the area? I keep saying it. How do you represent it? I think we already figured it out by now. So you just write the integral. You put the range, the bigger number on top, the smaller number below, and you put your function that you want to integrate. For example, maybe x squared, and you put your dx. That's how you integrate normally, right? Only thing with a range. So then the next step is to integrate it, like you would do normally. So for example, you get x cubed over 3. But in this case, you don't need to write the c, because your c will cancel out when you're doing the next step. So what you do instead, you put it inside a square bracket kind of thing, and you write the range on the right side of the square bracket. So you have a square bracket with x cubed over 3 inside it, and on the right you put your 2 on top, 1 below, for example. And then the final step is to calculate x squared over 3 for x equals to 2, and then also for x equals to 1. And then you minus for example, the one that's with 2 minus the one that's with 1, in a sense. So in this example, you would be like, 8 over 3 minus 1 over 3, and the answer would then be 7 over 3. So that's your final answer to the definite integral of x squared. So as I mentioned earlier, the c, let's imagine that actually is a c, and in the step where you minus it off, you'll be like 8 over 3 plus c minus bracket 1 over 3 plus c. So c gets minus off anyway, so you don't have a c anymore. You don't need to worry about it in the definite integral. But you must remember to write it once you get back to a normal integral without any range in it. So don't forget for just normal integration, but for definite you don't need to write the c. Okay, right. So that's how you find the area of, that's how you do it just finding the area under the curve until the x-axis maybe. Okay, but if there could be more than one way that the question is asked. If your curve is like this is for a scenario where the x squared is completely above the x-axis, except at x equals to 0, where it touches the axis. So the area that we are looking at is above the x-axis. So what if you're trying to find the area between the curve and the y-axis? Okay, so how do you do that? Well, you need to find what is the function in terms of y, I guess. Like you make x the subject. You make x the subject of the equation, and then you do integration with respect to y. And then you can find the area of the curve in between the curve and the y-axis. Okay, it's cool. For x squared, or other functions that are symmetrical about the y-axis, you should be aware not to use the wrong side of the curve. So if, for example, you wanted to do the positive side of it, you can use x equals to positive square root y as your integration for your integration. If you're finding it for the left side of the curve, then you should use x equals to negative square root y, and you will get you get one. If you use a positive one, you get a positive answer, then the negative one will give you a negative answer. So that's how it works. Okay, so that's for the axis on its own. What if you wanted to find between like there's one curve, but you don't want to find the area unto the axis, but to a line that's above the axis, or if the curve is below the axis, then the line is below the axis or something like that. Okay, let's just go with above the axis because that's less messy. So maybe you're trying to find the area in between x squared plus 1 and the line y equals to half. So you're not trying to find the line, you're not trying to find the area until the x-axis. So in this case, if you were to think about it in a very visual way, what's the best, how do you get the area? You just minus that rectangle that's underneath the line, right? You can get the area, the normal area as usual, just minus the part that has the rectangle. So how would you translate that into integration? Well, you can actually do a rectangle. You don't need to even include the y equals to half thing into the integration. You can just put like for example, if it's 1 to 2, right, then you can put, so your integration, the definite integral for x squared 1 to 2 would be 7/3, right? Then you can minus half from it, and then you get your answer. Or if you want to include it into the integration from the get-go, you can just put the integral as integral x squared minus half dx, and then you can just go on as usual. So yeah, that should be okay. But if the line is now a curve, and the curve is like, for that region that you're looking at, it doesn't intersect, you can just do the same thing, just minus it. Like, no, maybe if the curve is, I don't know, like let's say the one of the curves is like right below the other curve, then you can put the curve 1 minus curve 2, for example. But if it's like, if the curves are intersecting in that region that you're trying to integrate, you must first look at the question carefully to see which area that you're looking for. And you can use a bunch of techniques. One is addition or subtraction, based on, maybe there's one section where you, like, because different sections may have different integrations. You cannot really integrate everything at one go sometimes. Or if it's like, if you can integrate everything at one go, you can do that too. So you have to be a bit aware of how the area works, and sometimes you may need to do one that's in the x-axis and one that's with regard to the y-axis, and then you add them up in terms of the area. So you must be a bit aware about it, understand how where your area is, like where exactly the area that you're trying to find is. So maybe if you're a bit confused when you read the question, just draw it out or something if you're able to. Or if it's already drawn out, just shade the area that you're trying to find. And from there you can think of which what integrals you need, and then you start writing down the integrals carefully. Don't make careless mistakes. So yeah, that's just basically how it would work. I mean, I could show you an example, so hopefully I would have done that by now. So you can see you would have seen for yourself how you should go about doing it. Okay, so the next part is, so one of the points is about below the x-axis. So when you encounter area that's below the x-axis, or if you're looking at the y-axis to the left of the y-axis, you must remember to if you're trying to find the integral, then you can just do a minus. But if you're looking at area, then you must put a negative sign in front of the integral so that your minus will become positive in a sense, and you won't get your area minused off again in a sense. Yeah, just take note of that. Okay. So the next part is about parametric. Parametric curves. Sometimes you don't have a y equals to x something something, but instead you have y equals to t something something and then x equals to some other t something something, and you need to find the area. Well, if your curve is like very easy, if it's like very easy shape, then just use the shape like rectangle, triangle, that kind of thing, trapezium. But usually they don't just give you a nice shape or maybe some parts will be like a rectangle, some parts are a bit more like a x square kind of curve. So there's a bunch of ways that you can go about doing it. The first way is to actually, yeah, the first way is when you only have like rectangles and triangles, then you can just do that. The second way is to look to find the equation y equals to something something in x. And the third way is to look at the thing individually, in the sense. If you think about it, like you can find, you look at dt, then you use your dx or dt or dy over dt and then try to solve the integral that way. Like how we did substitution in the previous episode, the one with the sine theta, x equals to sine theta, that one. Likewise, you can do a substitution instead. And yeah, so those are the three ways that you can find the area. So the first way is rectangle, triangle. Second way is find the equation first. And third way is to do substitution. Yeah. Most of the time you'll be doing substitution. So yeah. Or if you're clever, you can do the equation one. I doubt you'll be doing only rectangles and triangles. There might be some sections with rectangles and triangles. And sometimes there might be a curve that has like multiple parts to it. They didn't really mention a point for that, so yeah, there might be a curve with multiple parts to it. And some parts will be just rectangles and triangles, and some parts will be like the piecewise function, that one. And some parts will be like the actual function, like some curve or something. And for those, you have to be very careful. And if you were to do it over a certain periodic range, you must be careful to see how many times you have to add that up, because if you don't do it correctly, then you end up messing it up in a way. Yeah, so just be careful about that. Right, so let's move on. So now we will get into the interesting part, which is the volume of revolution. Okay, I actually learned this in my secondary school advanced maths as well. I mean like RA, Raffles Academy. So I did learn about volume of revolution then itself. And I think that helps. But anyways, the idea of volume of revolution is you found the area, right? So now you just imagine as this shaded plane or like piece of paper or something in the shape. And then you decide to, and the paper has some kind of special paint that will stick wherever the paper moves. So now you rotate the paper throughout in one round, and the paint will makes one solid cylinder or something like that. And that's the thing that you're trying to find, the volume of this cylinder or whatever shape that is that you make by rotating it about the axis. So if you were to rotate it about the x-axis, obviously you have to do it with regards to x lah. If you do it about the y-axis, then you do it with regards to y. And you have to be very careful about which area you're trying to find, because sometimes they'll ask you to find the volume of like this shape that looks like a cone, which would be more of the y-axis, or volume of the shape that's outside the that's like the outside of that cone. Um, of course, you may say, oh, it regards to y-axis, but at the same time, you need to minus the x-axis one as well, or something like that. You need to do something to minus it off. No, you do it with regards to x-axis, and then then you do your volume with you do your pi thing to the y. Okay, I hope my image will be more clear in that sense. So because the part where you make it into a volume is not the same as the part where you find the area, in a sense. So let's say if you were to find, so you need to focus on which area you're trying to rotate to begin with. Yeah. So once you find that, you can then proceed to times it by pi. Well, because pi is like the circle, like the pi r square part of it, and once you times it by pi, you will get your shape, your volume of the thing. So for finding volume of your revolution, the main thing you need to remember is to put the pi before every integral. So whatever answer you get, you had to times it by pi. And also about which area is specifically that you're trying to rotate in this. Yeah, those are two things you need to take note of. Yeah. The final one is the final one is using a GC, which seems like the most fun, the most lazy kind of part of it, the most easy laid back part. Just use a GC, type some stuff, be like, hey, get the answer. For this, you just need to know where the integration function is. So once you find it, you can just type in the number, the range, as well as the function. And once you do that, you will get a value. As you can see, the graphing calculator is only useful for definite integrals rather than for integral in general. But if you want to get a general integral, then you can do the one where you plot a graph first, and then you can plot the integral of that graph. That's possible. If you want to, you can do that. But I'm not sure how that's gonna really help you. Unless you're very good at seeing the shape of the graph, then maybe that may help you. Maybe like for example, you suddenly forgot how to integrate x squared, then you can find the integral of x squared, and it looks like an x cubed curve. Oh, then you remember, okay, it's x cubed over 3, then you write it down or something. I don't know. I thought you would be in such a situation, but yeah. But for definite integrals, you can definitely use the graphing calculator. It has a function where you can just type it down. If you want to use the graph to find the value, you can first plot the graph, and then I think there's another function for which you can press to find the area under a certain part of the graph. Yeah, so in the menu you can go and find, I think it's in the mat list. I hope it's in the right one, because I don't remember how the GC works anymore. Yeah. Yeah, if you have any questions, or if you think I'm just saying some gibberish every now and then please type in the comments below, or PM me in Reddit or something, I don't know. If not, I would like to end by saying, if you enjoyed this video, you can press the like button or subscribe. And with that, I would like to say thank you and bye.